Hello everyone, dear student. I wish good luck, good health, and good energy. First of all, I shall give you some information about my lectures, this course of lectures. These lectures and other lectures you can find at my homepage, at my new official homepage of our the webpage of our university. So you can find metodyczni materiały, and here there are any courses which are needed in the Department of Mechanics, Mathematics, and in your department of the Applied Mathematics and Informatics. And today will be lecture number 5, Non-Deterministic Finite Acceptors. And after recording this lecture, I shall put this lecture on my website. So we shall start the lecture. So lecture number 5, non-deterministic finite acceptors. If you examine the automata we have seen so far, you will notice a common feature. A unique transaction is defined for each state and each input symbol. In the formal definition, this is expressed by saying that the transition function delta is a total function. This is the reason we call these automata deterministic. We now complicate matter by giving some automata a choice in some situation where more than one transition is possible. We shall call such automata non-deterministic. Non-determinism is a first sign and usual idea. Computers are deterministic machines, and the element of choice seems out of place. Nevertheless, non-determinism is a useful concept, as we shall see. Non-determinism means a choice of moves for an automaton, rather than prescribe a unique move in each situation. We allow a set of possible moves. Formally, we achieve this by defining the transition function so that its range is a set of possible states. Definition. And the non-deterministic finite acceptor was simply NFA by capital letters, is defined by the quintuple M. It consists of Q, sigma, delta, Q0, and F, where Q, sigma, Q0, and F are defined as for deterministic finite acceptors, but the function, transition function delta from the product of Q and sigma with the empty word to the set of all subset of Q, yeah. Note that there are three major differences between this definition and the definition of deterministic finite acceptors. In a non-deterministic acceptor, the range of the transition function delta is in power set 2 in power q, so that its value is not single element of the set q, but a subset of it. This subset defined the set of all possible states that can be reached by the transition. If, for instance, the current state is Q1, the symbol A is read and delta of Q1 alpha is equal Q0, Q2, then either Q0 or Q2 could be the next state of the non-deterministic finite acceptor. Also, we allow lambda as a second argument of the transition function delta. This means that the non-deterministic finite acceptor can make a transition without consuming an input symbol. Also, we still assume that the input mechanism can only travel to the right. It is possible that it is stationary on the some movies. Finally, in a non-deterministic finite acceptor, the set, which is an image of the transition function delta on QIA may be empty, meaning that there is no transition defined for this specific situation. Like non-deterministic finite automatas, deterministic acceptors can be represented by transition graph. The vertices are terminated by Q capital, while the edge QI, QG with label A is in graph and only if delta of QIA contains QJ. Note that since the letter A may be the empty string, there can be some edges labeled by empty set lambda. A string is accepted by an non-deterministic finite acceptor if there is some sequence of possible movies that will put the machine a final state at the end of the string. A string is rejected, that is not accepted, only if there exists no possible sequence of movies by which a final state can be reached. Non-determinism can be therefore be viewed as following intuitive instinct by which the best move can be chosen at every state. Assuming that the non-deterministic finite acceptor wants to accept every string. Example. Consider the transition graph in the figure. It is described as a non-deterministic acceptor because there are two transitions labeled by A out of Q0. So we have input state and two output states here. And all edge are labeled by the symbol A, yeah. The next example. And the non-deterministic automaton is shown in the figure. It is non-deterministic not only because several edges with the same label originate from the vertex, but also because it has empty set transition or lambda transition. Some transitions, such as delta Q2, are specific in the graph. This is to be interpreted as a transition to the empty set, that is delta of Q2, 0 is equal empty set. The automata accepted strings empty set, which is denoted by lambda 1 0 1 0 and 1 0 1 0 1 0, but not 1 1 0 and 1 0 1 0 0. know that for 1, 0, there are two alternative walk, one leading to Q0, the other to Q2. Even though Q2 is not a final state, the string is accepted because the walk leads to a final state. So we have a picture with this automata. Here is a input state and output state Q0, yeah. We have walk from Q0 to Q1 and Q0, yeah. And this automata accept only the word of the following form. If we input Q0, then we have no problem to output, yeah? And by this way, we get the empty word, lambda, yeah? So the next, if we make such cycle, yeah? Many items, we get the word of the form 1, 0 in power n, yeah? Also here we have a label edge, which is labeled by empty word. And here we have edge which labeled by 0 or 1, yeah. Again, the transition function can be extended so its second argument is a string. We require of the extended transition function delta star such that if delta star of QIW is equal Q capital J, then Q capital J is a set of all possible states of automaton may be in. Having started in the stage QI and having reached the word or string W, a recursive definition of the transition function delta star analogous to equation 1 and 2 is possible, but not particular angular tending. A more easily appreciated definition can be made through the transition graph. Definition. For a non-deterministic acceptor, the extended transition function is defined so that delta star of QIW contains QJ if and only if there exists a walk in the transition graph from the state QI to the state QJ, which is labeled by the string W. This holds for all states QI, QJ from the set of states Q capital and all string W from which is generated by alphabet sigma and empty set, an empty word or empty string, yeah. Example, the following figure represents a non-deterministic finite acceptor. It has several lambda transitions and some undefined transitions such that as delta of Q2A, yeah, we have input states, output states. Yeah, Q0 is input state, Q1 is output states, yeah. Suppose we want to find sigma star, delta star of Q1, QA, and the delta star of Q2 lambda. There is a walk labeled by involving two lambda transition from Q1 to itself. By using sum of lambda edges twice, we see that there are also walks involving lambda transition to Q0 and Q2. Thus, we get delta star of Q1A is equal from the set is here is misprint, must be that. Since there is a lambda edge between Q2 and Q0, we have immediately that delta star of Q2 lambda contains Q0, yeah? Also, since any state can be reached from itself by making no move and consequently using no input symbol, we get that delta star of Q2 lambda is also contains Q2. Therefore, we get that sigma star of Q2 lambda is equal similar from the set of states Q0, Q2. Using as many lambda transitions as needed, you can also check that delta star of Q2 AA is equal to the set Q0, Q1, and Q2. The definition of the generalized transition function delta star or transition star function delta star suit labeled walls in somewhat informal. So it is useful to look at it a little more closely. The definition 2.5 is proper because between any vertices Vi and Vj there exists as a walk labeled by a string W, or there exists no. Indicated that the transition function delta star is completely defined. What is perhaps a little harder to see that this definition can always use it to find delta star of QI W to find this image. Yeah, in the first lecture we described an algorithm for finding all simple passes between two vertices. We can not use this algorithm directly because, as example 209 show, labeled walk is not always a simple path. We can modify a simple path algorithm, removing the restriction that no vertex or edge can be repeated. The new algorithm will now generate successively as walk of length 1, length 2, length 3, and so on. There is still a difficulty. Given a string W, how long can a walk labeled be by WB? This is not immediately obvious. In example 208, the walk labeled between state Q1 labeled by A, yeah, between state Q1 and state Q2 has length 4. The problem is caused by lambda transition with lented the walk but do not contributed to the label. This situation is cited by this observation. If between two vertices y Vi and Vj, there is any walk labeled W, then there must be some walk labeled by the string W of the length no more than lambda capital plus 1 to lambda capital multiplied by the length of the string W, where lambda capital is a number of lambda edges in the graph. The argument for this is the following. While lambda edge may be repeated, there is always a walk in which every repeated lambda edge is separated by an edge labeled with a non-empty symbol. Otherwise, the wall contains a cycle labeled by empty word, which can be replaced by a simple path without changing the label of the wall. We leave a formal proof of this claim as an exercise. With this observation, we have a method for computing of the image by delta star of QIW. We evaluate all walks of the length as the most lambda plus 1 plus lambda multiplier of the size of the string W originating at the state QI. We select from them those that are labeled by the string W. The terminating vertices of the selected walk are the element of the set delta star of QI W. As we have remarked, it is possible to define the transition function delta star in the recursive fashion as was done for the deterministic case. The result is unfortunately not very transparent, and arguments with extended transition function defined this way are hard to follow. We prefer to use the more intuitive and more manageable alternative in definition 2.5. As for deterministic finite automatas, acceptors, the language accepted by non-deterministic finite acceptor is defined formally by the extended transition function definition. The language L capital accepted by a non-deterministic finite acceptor which consists the quintuple Q sigma delta Q0 F is defined as a set of all strings accepted in the above sense. Formally, the language accepted by M, it consists of the words from which is generated by alphabet sigma, such that the image of deterministic image of the function delta star of Q0 W intersects with F is not empty. In the word, the land will consist of all string W for which there exists a walk labeled by W from the initial vertex of a transition graph to some final vertex. Example, what is the landwidth accepted by automaton in the following figure? Here we have input state Q1, this state also is an output, we consider this graph in previous example, it's easy to see from the graph that the only way from the non-deterministic finite acceptor can stop in a final state is if the input is either a repetition of the string 1, 0 or the empty string. Therefore, the automata accepts the language L capital, which considers power, any power of the string 1, 0. What happened when this automaton is presented by the string W, which is equal 1, 1, 0? After reading the prefix 1, 1, the automaton finds itself in the state Q2, yeah? With the transition delta of Q to 0 undefined, yeah? We call such a situation a deed configuration. We can visualize it as an automaton simply stopping without further action. But we must always keep to meet that such visualization are imprecise and carry with them some danger of missing interpretation. What we can say precisely is that delta star of Q 0 1, 1, 0 is equal empty set. Thus, no final state can be reached by the proceeding of the string, which is equal 1, 1, 0, and hence the string is not accepted. In reasoning about non-deterministic machine, we should be quite cautious in the using intuitive notion. Intuition can easily lead us astray, and we must be able to give a precise arguments to substitute our conclusion. Non-determinism is a difficult concept. Digital computers are completely deterministic. Their state at any time is uniquely predictable from the input and the initial state. Thus, it is natural to ask why to study a deterministic machine at all. We are trying to model a real system, so why include such a deterministic future as choice? We can answer this question in the various ways. Many deterministic algorithms require that one make a choice at some stage. A typical example is a game planning program. Frequently, the best move is not known, but can be found using an exhaustive search with backtracking. When several alternatives are possible, we choose one and follow it until it becomes clear whether or not it was best. If not, we retreat to the least decision point and explore the other choice. And deterministic algorithm that can make the best choice would be able to solve the problem without backtracking. But a deterministic can be simulate non-determinism with some extra work. For this reason, non-deterministic machine can be served as modulus of search and backtrack algorithms. Non-determinism is sometimes helpful in solving problems easily. Look at the non-deterministic finite acceptor in the figure, in the following figure, yeah? It is clear that there is a choice to be made. The first alternative leads to the acceptable of the string a in power 3, while the second accepts all string with one even number of a's. The language accepted by these non-deterministic finite acceptor consists of the following sets: the single string a in power 3 and the string of the form a in power 2n, or the whole string. Yeah. While it is possible to find the deterministic finite acceptor for this language, then determinism is quite natural. The language is the union of two quite different sets, and the determinism let us decide at the outset which case we want. The deterministic solution is not as obviously related to the definition, and so is a little harder to find. As we go on, we shall see other and more convincing example of the useful of non-determinism. In same vein, the non-determinism is an effective mechanism for describing some complicated language consequently. Note that the definition of the grammar involved non-deterministic element. In this function, S into S, A as B restriction lambda, we can at any point choose either the first or the second production. This lets us specify many different strings using only two rules. Finally, there exists a technical reason for introducing non-determinism. As we shall see, certain theoretical results are more easily established for non-deterministic finite acceptors than for deterministic finite acceptors. In our next major result indicated that there exists no essential difference between these two types of automata. Consequently, allowing non-determinism often simplifies formal arguments without affecting the generality of the conclusion. So I finish my lecture. First of all, I recommend you to write me a letter on my mail of a yahoo.com that you listen my lecture. I wish you good luck, good health, and ending of this war with Russia. Goodbye and good luck.